All right. Okay. Welcome everyone. I just continue, but I will not repeat. But if you have any questions, please you can ask me and please stop. Okay, anytime. Right. Okay. Before this, I think the slide and sound, the setup, everything is clear. Is it?
Yes, doctor. Clear.
Okay. Thank you. I'm not sure whether anyone is waiting in the. I don't know. It could direct to attend, but anyone is waiting in the room or not? I think no one is waiting at the moment. Okay. Every time I change the window, then we need to reconnect to the things. Okay, fine. Okay. Okay, we can. Today, actually, I will discuss actually some analysis. I discussed some basic. Hope you have understood something, but I will repeat sometime. Okay, when I need. Okay. So actually, groundwater hydraulics. This is actually I will start now. So when we do the groundwater hydraulics, actually basic understandings that we need, we discuss something. How is the aquifer system? Okay, all of the things. Okay, so when I do the groundwater hydraulic study, so first thing actually we need some data. We need some data. So how we can get the data? Okay, data we can get from some secondary data. If let's say if someone has did some pumping test, okay, that pumping test data, then we can collect the data, then we can do the analysis. Okay, that is the one thing. Secondly is we can collect ourselves. Okay, we can collect from the field direct. Okay, so that test is called pumping test. Okay, when we this is the pumping test. So when you do the pumping test, actually all the required data we can find to do to study the hydraulics, groundwater hydraulics. All right. Okay. So what we need actually when we do the study, actually this is some setup. Okay. So you can see this is the groundwater oil. This one. Okay. The T well. Okay. So this is the discharge. Okay. So when we do the pumping test, we must know what is the Q. How much the Q? This must be known. Okay. So now we have a different types of modern devices that those devices we can use. Okay. When the water is flowing through the pipe, so we can set up some device. Okay. Then we can know what is the Q. So this is actually that is a flow meter. Okay. So sometimes if we don't have a flow meter, because flow meter is expensive actually, all flow meter very expensive. Okay. So then the alternative option is, I think all of you are well known about this. We can use the V notch. Okay, 90-degree V notch. This is the 90-degree V notch. Okay, So if we know this 90 degree, if we have this 90-degree Venus, so simply, if, actually there is a simple formula we can use. Okay, 1 point. I think this 38, then is 2.48. Okay, if we use the 90-degree Venus. Okay, so we just need to make we just need to at this height. So this is very easy. So meaning in that case, so this is the flow. So this flow, when it drop on the ground, so we have to set up Venus here. Okay, so meaning that water will flow, then we can get this ace. Once we know this ace, we can calculate the Q. So this is the manual technique. Okay. So, but if we have some device like sensor type and data logger, then we can keep the record continuously. Okay, this is the thing. That is the Venus. Venus means this is actually oil. Okay, and then some volumetric method, Peter tube. So these are the options we have. We can know this Q. Okay, so this is a part of hydraulics. I think all of you know. All right. Okay. Secondly is this is the Q. That this is the method we can know the Q from this pump. Okay, and then water level. So when water is flowing, we need to measure the water level. Water level, why? Water level in the groundwater level. Okay, this is the actually groundwater level. Okay. So groundwater level we can use with the different techniques. So most important, most easiest way is using this kind of sensor. Okay, this very accurate because it has connected with some wire, and we have a display unit. Okay, so this one has a sensor at the top. So once this one we just drop in the oil. Okay, like this. This is the oil. So this is the water surface. So when I drop down this one, it touches the water, it makes a sound. So we can listen the sound here. Okay, when you listen the sound, actually we can see what is the height. Okay, from here to here. Okay, so this one we can measure. Okay? Because this one actually we measure from the beginning. Okay, meaning that when we this one is very simple. Okay, sorry, I draw here. So if I draw, you will understand better way. So this is the water level before pumping. Okay, before we start the pumping. So this is the initial reading at T0. Okay, T equals 0 means before pumping. So once we start pump, so first we read this one. So we using this sensor, we read this value, meaning that at T0, when the 0 time, what is the water level? Okay, so we measure the water level. Let's say water level is here 8. Okay, suppose 8. Once we start the pump, immediately, I mentioned before, immediately the water level will drop like this. Okay, so water level will come down here within a few seconds. Within a few seconds. Okay? So then we will start maybe every 1 minute. Okay, after 1 minute, we'll take the second reading. Then maybe we can find the second reading, maybe like, let's say 13. So it is a 13. Okay. So this is the way actually we can get the water level. So if this one is 8, so this one is 13. So meaning that the drawdown is now 8 and 13 is 5. Okay. So this term is called drawdown. Okay. So this drawdown we define as SW. SW means S is a drawdown and W means oil. Okay. W usually we use as oil. So SW means drawdown in the oil. Okay, drawdown in the oil. So this is the pipe. Okay. So once we start pumping, we continuously we monitor this level, okay, with this sensor. All right. So this is the use. We do pumping test this. Okay. So meaning that pumping test actually we collect the Q and we collect the dot means water level. Actually, when we know the water level, so from the difference we can find the drawdown. Okay. All right. So meaning that we have a Q. So we have a Q. So Q, we keep the Q fixed means constant. Okay. Q will be constant. Okay. With constant Q, we will continue pump something like I mentioned yesterday, 1 hour, 2 hours, 3 hours. We can go 6 hours. Okay, depending how this one is changing. Okay, if this one is continuously changing after 1 hour, 2 hour, we will continue. Okay, if it doesn't change, then we will stop. Okay, so Q will be constant with Q constant. Okay, so we have a time, and then we will measure the water level. So this is the job mainly. So start from 0, 1, 2, 3, 5, 10 minutes, 15 minutes, maybe 20, 30, then 45, 60, 75, 90. Once go 90, maybe we can go maybe every 30 minutes. Okay, like this. Because when time passes, this drawdown, okay, the water level, the changes will be very small with the time. So that's why after sometimes we will go longer time. If after 30 minutes, let's say 120, 150, still this one is changing, maybe next one we can go after 1 hour. 1 hour. So if we see this, if after this there is no changes, we can stop it. That's all. Okay. So meaning that at after certain time, we will start pumping, but this drawdown will not change. It will be constant. So this at this time we call equilibrium. Okay, equilibrium condition. Equilibrium condition means that we are pumping, but level of water doesn't drop. It in out balancing. That is called equilibrium. Okay, equilibrium condition. Okay. So we want this. So this equilibrium condition, if we can get very fast, how quick we can get it, then we can say this pump is very good. If we get after a long time, meaning that the aquifer is not very strong. Okay, so in that case we cannot increase the pump, the Q. So in that case, the more I think recommendation is the reduce the Q. Let's say we had a initial Q was 22.5. Maybe we can reduce to 2. Okay. Some if we decrease the Q, then this equilibrium condition will improve. So meaning that we can get early. Okay. This is the some recommendation, because I mentioned yesterday that always when you do the pumping, we have to think about the safe yield. Okay, safe yield. So we should not go for over pumping. Okay, so meaning that if we don't get the equilibrium condition, so meaning that actually this means that we are doing over exercise, means over pumping. Okay, over pumping. So recommendation is the test. Okay, pumping rate. If we reduce the pumping rate, so then I believe that we can get the equilibrium condition um, sometime before. Okay, that's the thing. All right. Okay, so this then once we get this data that I mentioned, the time and water level, when we get this data, so this data we can get from the direct experiment, or we can collect from the some secondary data. Then these are the techniques we use. Okay, all of these techniques. The TESS method. TESS is the first method that I think told yesterday, and then these are the other simplified methods. Okay, so I will try to discuss all of this then actually you will at least understand that how we can determine the Q from the groundwater. Okay. Or whether it is safe or not also, because sometimes if we don't have understanding, actually groundwater pumping is difficult because we cannot see what is, it is invisible sources. Okay. But we have to practice with science and techniques and understanding. Okay, so this is the figures that I showed before. So actually this is the just a sequence. When we before start pumping, so this is the water level. Okay, before we start. So water level is this is the before pumping. So once we start pumping, so this is starting. Okay, so that gradually it will drop like this. Okay, then gradually this will by time it drops. Okay, this is the symbol showing. So here we have some technical term. So please understand this one. So you have to remember this. So once you understand this technical term, so it would be easier for you to read any documents. When you read, then we can understand. Okay. So this is the upper layer of the aquifer. Aquifer is, so in this case, this one is a confined aquifer because the upper layer is a this is an impervious layer. Okay, or maybe this impervious layer, down also impervious layer. Okay, so this is a impervious layer, actually this color one. Okay, this one. So this is the impervious layer, impermeable layer. Okay, so this impervious layer means the water cannot penetrate here. Okay, on the top. That's why it is a like sealed, totally sealed, like a floor. Okay. Okay, so when we penetrate the oil, so this is the aquifer. So this aquifer is called confined aquifer, and this is above this part. This is unconfined. Okay. Unconfined. So unconfined aquifer is the characteristics of unconfined aquifers like a open channel flow, and the confined aquifer is like a pipe flow under pressure. Okay, this is the thing. All right. Okay. So then actually once we start pumping long time, then it will develop this kind of cessation. Okay. Okay. So meaning that this is the original water level. Sorry. Yeah. This is the original water level, and this is the final water level. So this difference we call SW. Okay. So we have here 3 pipe. You can see here 3 pipes. So this is arrow. You can see this arrow. So meaning that this is the discharging oil. Discharging oil means this is the main tube or pumping oil. Sometimes we call discharging oil, sometimes we call pumping oil. Okay, is the same. Okay. Also we call tube oil. Okay. Sometimes simply we call oil. So actually all of these are same terms. Okay. Tube oil, then pumping oil, discharging oil is the same. Okay. Beside this, we have another pipe. You can see. Okay. So these two is called observation oil. Okay. Observation. Sometimes we call also monitoring oil. Monitoring oil. So monitoring oil or observation oil, we can have a more than 2, 3, 4. We can put it. Okay. So normally we put in one side. If we have more oil, we can also put this side. No problem. So the regulation is the regulation actually when you install the observation well, this one is very important also. You can see the pumping oil, this pipeline, and you can see the level. So observation oil should be the same level. Okay, this is the principle. We cannot install like this. At a different means the depth should be the same. Depth should be the same. All right. When we have a same depth, then what is the influence in the pump? Then we will get the same influence in the monitoring oil. Okay. All right. So drawdown in pumping oil we define by SW, and the drawdown here you can see this one. Okay, so meaning that from here to here, this one. So this is the drawdown here. So observation oil drawdown we define by S1, S2. If we have a two observation oil, we can S1, S2. If we have a three, S1, S2, S3. Okay, like this. All right. So this is the this is the way. So meaning that when we have this setup, let's say we have this setup. So when we collect the data, how we can get the how we can get the data. So data collection is the same way. So we have a time here, time. So this is the water level at, we can say water level at pumping oil is SW. Okay, means drawdown, and we can say drawdown means S1. We can say S2. Okay, so S1 means this one is S1, this one is S2, and this one is a pumping. So we'll know that this water level. So you can see the when water level is pumping here, here is here. So it can change. If it change here, so this one will change also. So this way we will collect this data. So taking the pumping test, we will do these activities. And remember that when you install the monitoring oil or observation oil, okay, okay, just a minute. It shows that my battery is, so I have to connect with the power. Just a minute. Okay. I wish it can find properly. Okay. So this is how we can collect all the information. All right. I think I forgot where I stopped. Anyway, no problem. Okay. Okay. Can you hear me?
Yes,
Okay, can you
doctor.
see? Okay. I don't know what
Mm.
something happened suddenly. Suddenly the
But
I
your video not moving, eh?
sorry.
But you not moving, doctor.
No, I don't know. Suddenly my means laptop screen was blackout. I don't know. I thought it is a battery problem, but okay. I think I hope I believe everything fine now. Yeah. So you can see this thing.
Yeah, doctor. Okay.
Fine. I can listen your sound. All right. Let me set up first again. So there's something happened. With the moving, but it needs to set up again. Okay, something is a slide is moving, but there is something is okay. What you can see now? I just want to confirm. So my slide is moving or not?
Yes, doctor. Moving.
Okay, but it is not as before. I don't know. This is something. Just a minute. I can see, but actually I'm trying to display on my iPad. Okay, so yeah, I think now is okay. Is something is okay. So anyway, so this is the cone of depression, meaning that when we start the pumping, okay, when we start the pumping, this is the you can see this curve. It automatically will create. Okay, it will create. Actually, there is some problem. Actually, I am not sure. You can see if we click here, this one is inactive. I don't know whether it will fix or not. Okay, please start. No problem. All right. So this is another figure. So actually, this is the pumping oil, or we call discharge oil or recharging oil. So we have, this is the monitoring oil. Okay. So we have a different types of aquifer. Okay, oil. We call confined, unconfined. We have fully penetrating. We have partially penetrating. Fully penetrating means the pipe is penetrated to the full thickness. The okay, so this is a sorry, this is a thickness of the aquifer. So when we install, or when we install the pipe in the full length, we call fully penetrated. And sometimes we can have it just half or one third, we call partial penetrated. Okay. This one we are familiar with this. This is called dark well. Okay. So normally in the village or rural areas, we have this one. Okay. So now I am moving. There is a some defined setup of the T well. Okay, so here is showing all this. This is called static water level, and this is the depth of water when we measure. These are called cone of depression. So this line, okay, and this is the pumping level. Means when we pumping, then what is the water level? So that is called pump water level during or at the pumping time. Okay. Okay. So here is a same thing. Here is a static water level. So meaning that this is the static water level at the beginning. Okay. And then pumping water level means when it start pumping at any time, what is the current water level? So that is called pumping water level. And we call drawdown. Okay. So drawdown is, I mentioned here, drawdown, that drawdown, this one we define as SW. Okay. So sometimes we can measure the SW. Here is, you can see H minus H. So meaning that H total, and this is the difference. So H minus S is S, this one. So this S means actually observation oil. Observation oil. Right? And H, this total H minus the aquifer thickness here, B. This means drawdown in the pumping well. So this is the how we can determine this thing. Okay, I just explained this one when we have water level at a different time. So how we can determine the drawdown. Sometimes we can determine the water depth. Okay, we can do this. Let's, so this one is I have already explained. Okay. So now we come to what oil hydraulics. Okay. Okay. So oil hydraulics, actually the theory is quite complex because we have some differential equations. If we have a differential equation, but normally groundwater flow is a partial differential equation because it is a multi-directional flow, two-dimensional, three-dimensional flow. It is not a one-dimensional. Okay. So that's why the equation is a partial differential equation. So originally the groundwater equation is a partial differential equation. So we have a first order, also we have a second order. Okay, so this is the original equation. So by numerical analysis, we can solve this equation. So after solving, we can simplify to the simple mathematical form. Okay. As I mentioned yesterday, that these are the, when we do the pumping test, easily we can collect all of this information. Okay, we can collect it. Okay, we can collect all of this information, but when you do the water groundwater hydraulics analysis, we don't need all of this. We need the K, we need the T, but this T and S, this T and S, actually this T and S we will determine. Okay, we'll determine T and S. So now this is the different methods we have. Okay, there are number of methods. So groundwater hydraulics that we discuss now, groundwater hydraulics, all right. Okay. What is the purpose of this? Yeah, purpose is we do the analysis. What we analyze? We analyze the time drawdown. Is it water level? Actually, drawdown is a water level, depth of water level or change of water level. This is called drawdown. So we actually collect the data with the time, with the water level in the oil or observation oil. We have two types of oil. One is observation oil, another is a pumping oil. So we collect the data in the pumping oil or also observation oil with the time. And this data we analyze. Okay, we analyze this data. Okay, now it is okay. We analyze the data. What is the purpose then? So main purpose of this, we determine the S and T. Okay, these two parameters, mainly these two parameters. S is the storativity. Okay, I explained yesterday. Storativity, and this one is a transmittivity, double SBITA. So S denote the amount of water that can pump, okay, by unit changing of drawdown. 1 meter, 1 meter drawdown from 1 meter square of aquifer. Okay, so if 1 meter square aquifer, when drawdown change from 1 meter, let's say this is the original water level, and come down to 1 meter, and the area is 1 meter square. So how much water is available can pump? That is denoted by S. And T is when S is we can pump. So how is the how the water moves in the aquifer? Okay, how fast or how good the water transmit? Because inside we have the rock, is it? Rock. So water moves. Okay, water moves through the rock. Okay, so how move the water transfer? So this is the two important parameters. Okay, so these two parameters is one is S, another is T. So by hydraulic groundwater hydraulics analysis or oil hydraulics analysis, actually we determine the S and T. Right? This is the main purpose. Once we know the S and T, then we can know the we can characterize our aquifer. You can see the all of these techniques. This is the summary of the techniques. It is the Q, and then we have the, you can see this is the T, and here is the S. Okay, so we have a two S's here. One is capital S, another is a small s. So when you write, be careful. So normally I write like this. If like this, it is a storativity, and if I like this, so this one is a drawdown, S1, S2. I like this. I use right, but your case, yes, you will define. Okay, because in the groundwater book is capital S and small s. Okay, so be careful. Okay, you can see here, even here, you can see this is a capital S, this small s. So this is the capital S, and this is the small s. This one is a small s. Okay, right, this is the T. So we have a two S. Okay, so be careful. So one in the observation oil or monitoring oil or pumping oil drawdown, another is the storativity, different things. Okay, so this we have a different methods. Okay, and then you can see here T and S. How we can find T and S? So this is the mainly we hydraulics. So we have a different techniques. So I believe no technique is perfect. Okay, no technique is perfect. Perfect means not 100% accurate. There will be some differences, but we can once we use different techniques, so we can confirm which one is more accurate. Okay, because we can evaluate with the pumping the Q, because once we know the S and T, then we can calculate the Q. Okay, so this Q is calculated Q, and we have a actual Q. Actual Q means that is when you do the pumping, we can measure. Okay, so this actual Q and this Q, calculated Q, then we can see the differences. When difference is 0 means perfect. All right. So that's why no method is perfect, but we can confirm which one is the best. Okay, now we can come to one by one. How we can. So first, you can see we have a different condition. This is a steady flow. Okay. Steady flow in unconfined aquifer. When you say unconfined aquifer, it means that we have a permeable layer and the oil is like this. Okay. So this is the original water level. So once we start pumping, so this water level will come down. Okay. This is called unconfined. So unconfined aquifer, I mentioned that unconfined aquifer, the characteristics is it is like an open channel, so meaning that water level remain the same. Okay. The original water level in the pump and original water level in the soil underground is the same level. This is a, then we can understand this is the unconfined aquifer. Okay. So meaning that if we have the observation oil here, this is the pumping oil, this is the observation oil at the beginning before pumping. So before pumping, here and here is the same. Water level will be the same. There is no difference. Okay, no difference. Okay. All right. So at the surface of this here, so water pressure is 0 because this is the atmospheric pressure of here. So this is the unconfined. So this is called unsteady, unconfined aquifer. So when we have unconfined aquifer, so this unconfined aquifer sometimes also we call water table condition. Means what is the groundwater table? Means water table, groundwater table, or we call saturated. Okay, another one is called saturated water table. Okay, saturated or groundwater table. So it is the same as unconfined water table. Okay, so this one in this case it is this one. Okay, this is unconfined. So from here we have to understand all of this notation. What happened? Okay, I just explain one, then later you can understand all of this thing. Okay, it would be easier for you. Okay, I make it a little bit bigger. Okay, okay, this is, you can see this is a when we see this kind of drawing, so this meaning that this is a impermeable layer. Okay, we call impermeable layer. Okay, so this impermeable layer in groundwater technology terms we also call aquiclude. Aquiclude is something like a hard clay. So this kind of texture or soil structure, it doesn't allow water to penetrate. Okay, it is like a seal, very like in the civil engineering we call bento tight. Sometimes we need to seal the soil surface or something, so we can the clay. Okay, in the very small clay type. Okay, so it's called impermeable. Alright. Okay, so then this is the pumping oil. So we can understand the pumping oil, how we can understand. So usually in the drawing, you can see here Q, this one. Either this way or sometimes it can be written like this, the top. Okay. So this is, then we can say, okay, this is the pumping oil. Okay. So this is the ground surface, written here, ground surface. And this is the before pumping, this is the no pumping water level, means before pumping, this is the water level. Okay, so when we start pumping, so this is called T0. When T0, okay, meaning when T equals to 0, so this is the water level before pumping. So once we start pumping, so water level will drop. It comes to here. Okay, so this comes to here. So this is called drawdown at this time. Okay, at this time, drawdown in the pumping well. Then we have a observation oil. Observation oil means this one and this one. So we mentioned is it maybe S1, S2. So here is, you can see here, this is the original water level. So from original water level to the bottom of the aquifer, this is called H1. And here is called H2. Okay. And ASW, this is the drawdown, means original water level to this level in the pumping water level. Okay. This is called SW. You can see here from here to here. This is the SW. Okay. So when we start pumping, then this is the water level in the pump will be lowest. Okay. This is the here. And we have the cone of depression like this. So it will create both side. Okay. It will create both side. So what is in the observation well? This is the observation well O1. So here is called S1. You can see from here, this side. Okay, this S1. And then this one is a small, very small. So it is S2. Okay, so we can have a more observation well, and sometimes we will see that there is no change. Okay, if we do something, let's say 100 or 200 meter or 150 meter far away, if we have the observation well like this, then we will see that this observation well, there is no change. It is the same as water level in the pumping. Okay, the last one. So when we get the same, so this is called radius of influence, means when water level is same in the observation well. So this radius, this is called radius. Is this why radius? Because this is the circle. This is the circle. So this one is called radius. Actually, this is a big circle. Okay, big circle. Okay, then we have a dx dy. You can see a dx dy. Dx dy is actually we can so here I just erase it, make it clear again. So this dx dy, so it is any point in this, sorry, any point of this line, this cone of depression, any point. Okay, so if we take any point, so the distance from the pump, this is called x, and this is called y. Okay, these are things. And dy dx, that is mentioned here, dy dx, dy and ds. So this is this changes, means the rate of changes. Okay, is the dy by dx. Okay, because when water pumping, so this cone of depression, you can see the slope. Okay, this changes is dy dx. Okay, and that point, any point we take, this is the x distance and y is the vertical distance. So this is the all the notation, and here is this one is called screen. So meaning that water from the aquifer enter into the oil, then it goes. Okay, so this this is all of this notation, and another one is in the oh, okay. I explain this one, then rest we can know all this notation is the same. Then we have the RW. So RW is the diameter, is the radius. Okay? It is the radius of the pump. Okay. When you say RW, it is called radius of the pumping oil, means that actually the diameter of the pipe. Okay. Radius of the pump oil. So this half. And then when we use this one, where is this? R1, R2, you can see here, R1, R2. So meaning that this is the distance. This is the distance from pumping oil to the observation oil, first observation oil. R2 is pumping oil to the second observation oil. So this is R1, R2. And when R1, it is a H1. When R2, it is H2. Okay, H1, H2. And HW, there is another term is called HW. So HW is the, you can say it is a skin depth, not the skin depth. It is called, when we start pumping, we have a cone of depression. Okay, so where is the water level at any time? So from there, the bottom of the aquifer. So this is called HW. And from original water depth, and this one is called SW. This is called SW. And so this HW and SW. So actually, this is the H. H equals SW plus, sorry, SW plus HW, H, the capital H. And PWL means pumping water level. This PW means pumping water level, means current pumping water level. So because when we start pumping, this pumping water level is always, it is a dynamic. It fluctuates all the time. Okay, until it remains with the equilibrium condition. Okay, otherwise it will be continuously changing depending on the Q. Okay, so again, what I say equilibrium condition? Equilibrium condition means when you start pumping, after sometimes it can be maybe any time, maybe 15 minutes, 2 hours, 5 or 6 or 6, depending on the aquifer characteristics. When we continue the pumping, but this level, it will remain constant after sometimes. Okay, so that time we call equilibrium condition, that condition. So that is the maximum drawdown. Okay, this is our maximum drawdown. Once we get this maximum drawdown, then we can find this characteristics Q by SW. Okay, so this Q and SW we call specific capacity. Okay, so SW is small, the pumping condition or aquifer condition is more better, more strong, or we can better aquifer. Okay, so sometimes equilibrium condition can be here, here. So different places will be different. It depends on aquifer conditions, aquifer characterizations. Okay, so that aquifer characterization actually we can, how we can know, how fast we can get the equilibrium condition, that depends on S and T. So meaning that if our S is good, T is good, we get this equilibrium condition faster. Okay, faster. So that's why when we do the pumping, we must know the, what is called, we must know the S and T. Once we know the S and T, then we can find how fast or when we can get the equilibrium condition. Okay, so meaning that we can get the maximum drawdown in the oil. Original water level. So this one is small. Our aquifer condition is good. When aquifer condition is good, means S is good, T is good. Okay, so once we know this, we can determine what is the pumping maximum pumping capacity, or we call safe pumping. Okay, safe pumping. Sometimes we call safe yield. The technical term is called safe yield. In this case, yield means actually the pumping rate. Pumping rate. Yield means because it is a oil, so how this called outcome is it production. So that's why it called safe yield. Safe pumping oil, maximum pumping oil, optimum pumping oil. So all of these terms are the same. Only one condition: the rate at which there is no negative impact in the environment. So that is the pumping oil. So that's why we need to study hydraulics, and we need to know the AST this. Okay. So then we will do one by one now. Okay, right. Okay, do you have any questions now? What I explained? Because I explained this one because this notation will be used all the time. Only difference will be for confined aquifer. Instead of here this, we will use the B. Okay, I will explain that time. Do you have any questions? Yeah, anything that you confuse or not clear?
No, sir. Okay.
Okay. Okay, thank you very much. Okay. Actually, I'm not good in this online lecture for this, especially for this topic. If the whiteboard, I could draw myself. I could explain better way. Okay. I cannot write faster here because if I write faster, then the system can stop. I don't know. Sometime. Okay. Anyway. Okay. So this is the theory. So I don't explain the theory how to derive this equation. Okay. I just simply give you some understanding. Then you can. I hope you can understand this one because you have studied this one before, maybe in other subject. Okay. This is the Darcy's equation that we know that Darcy's equation is velocity equals Ki, is it? So I think civil engineering always study this one because this is the flow, water flow through the porous medium, and the negative sign means the flow direction is from high water level to low water level. That's why we use the negative. Okay, and I is the gradient. So what is the velocity? It depends on the gradient. Okay, and K is the conductivity. So in this case, our case, K conductivity, because confined aquifer, unconfined aquifer, this is a porous medium by soil, rock, sand, coarse sand, gravel. Okay, so we use this conductivity and also use the hydraulic gradient. So we use the Darcy's in the groundwater. So if we use the Darcy's, so this is the velocity. So we know that Q equals AV. This is the general formula, is it? Q equals AV. So then our V equals minus Ki, and A is the area. So this area means, now I need to show you. So this area means this one, the area of this. You can see this is the radius of influence. So this is the one diameter. This is the half. This is the radius. This is the radius. So if we make the circle like this, just imaginary circle. So this is the surface area. So this surface area, we know that this is 2 pi r. Is it? 2 pi r is the perimeter multiply by the height. Okay, 2 pi r square for perimeter, and the volume is 2 pi r multiply by area. Okay, multiply by area. Then we can get the volume. Okay. So in that case, if we see this one, so it becomes like this kind of area. Okay, area. So this area, and I mentioned here this any point of the cone of diffraction. This is dy dx. So that is actually here use the same thing. Okay. You can see here when you use the k here, this is the k. Dy dx is the gradient, and this is the 2 pi x y. So it means that this is our oil. So this one. So any point, if we take this, so this is the x, this is the y, and this point is our gradient dy dx. All right. So this is the 2 pi. This is the radius 2 pi, and this the y is the height because it's a very small. Is a very small. So the small diameter, then also the height. Okay. So this is called this. This is called 2 pi. 2 pi x is the maybe meter, and y is the meters small thickness. In this case, y is the thickness of the aquifer, a small slice. Okay. So then this is the area. So then when we get this, then we can sorry. So how this q, right? So we get the k gradient from here, is it minus k I a. Okay, from here. So k is this, I is the gradient, a is the area of that small slice at any point. Okay, here. So then actually, if we have this one, then we do the differential equation. We can solve it. This is called something called separable. Okay, separable method. So we can have a q. Another side is this. So we put x and y left and right side. X means if we see here x, and we have the observation oil. Is it? This is the pumping oil. So first observation oil is R1. Second one is R2. That's the limit is R1, R2. And the Y is first observation and pumping oil. This is on H1, another one H2. I mentioned before. So this is the limit H1, H2, H1, H2. So when we do the integration and I put the limit, then we can get this equation, right? So this is the way actually we derive the all the formulas. Okay, means groundwater hydraulics. We can derive all the formulas. So I will not explain the how to derivation, because if I explain the derivation, I cannot show you uh, many, maybe one or two. Then I can have to stop it. Okay. So this is the I just explain you. So actually, finally, actually we need to know what is this. Okay, this one. Okay. So meaning that from this formula, you can simply understand here. Previously that I explained all the notation is it. You can see the Q. So when we have observation oil or pumping oil like this is the pumping oil, then this is the observation oil 1 and 2. Then you can see the Q. So this Q, this pi and K. Pi is constant. K is a we have to find by experiment, because the aquifer materials, as I mentioned yesterday, we have to bring. This is our aquifer, is it? Our aquifer is here. This here. So this material we have to bring to the lab, and we have to do the DASIS, that experiment. Okay, then we can find this K permeability, falling head or constant head. Okay, we can find the K. If K is available, it's fine. Okay, then once we have the pumping, so we have the observation oil 2. So then we can know this H1, we can know this H2. Okay, so this is the H2, H1. And from pumping oil, this is the R1, this is the R2. So R2, R1. So when we do the pumping, even with like water is pumping, but we don't know how much is Q. But if we have this information from the monitoring oil and here, so this formula will give you what is the Q. Okay. So Q we can find two ways. Okay, you can see here. This one means we have we have the information from the observation oil H2, H1, R1, R2. We also get the Q from the pumping oil. Okay, when you say the pumping oil, instead of H2, we use the H and HW. What is the H? H is this is the pumping oil. This is the pumping oil. Okay, this is the water level when pumping. So H is the original groundwater level, original groundwater before pumping. Okay, so that is the H. So this one is from here to here. H. And what is the HW? HW is this one. So actually this H minus HW, this one means actually this one. So this is actually drawdown in the oil. And what is this capital R? Capital R is when we have this, so we have the cone of depression like this, is it? This one. So this here to the original groundwater level. So this is the R. Okay. And RW is the diameter of the oil. So this is the two ways we can find the Q. Okay. So I already explained the notation. So now if you know the any formula, then you can find what is this. Okay, you can see here, from here. All the notation is available now. You can see here H. This is the HW. H minus HW means SW. Okay, H1, H2. So first you have to understand all of this notation. What is this? What is this? Okay. Then we derive this formula. Second step is we derive the formulas because we don't have a time. If you want to derive the formula, this groundwater should be the whole semester. Okay, then we can derive it all one by one. Okay, so then you can find the Q. You can find this one also. You can find this one also. All the information is available. So using this formula, you can calculate the Q. Once you calculate this Q, this is called calculated Q. Now we have the pump. You have the pump. So when it is pumping, then this is called pumping Q, discharging. So this Q, we can observe, we can measure it. We can measure by different device, pumping flow meter or orifice or OM that I explained in the beginning. So this is called Q actual. So then this is the estimated and Q actual. Then you can see, okay, this is the estimated, okay, estimated or calculated. Okay? Q equal calculated or estimated. So this Q actual and Q actual, what is the difference? If difference is very small, 1%, 2%, 3%, meaning that your FIFO setup, everything is fine. Okay. So this is how you can find the calculation, how to determine how to calculate the Q for unconfined aquifer. So clear this one. Do you have any questions from this explanation? So can you hear me? Okay, good. Okay, so this one, this part is actually nothing. This part is just some simplification from here. A square minus HW square. So A square is W square. This one is some formula, is it? S plus HW H minus. This is algebra. Okay, so this when this one is uh, 0 means H means drawdown is small. So H and HW is the same. Okay, because you can see here, if drawdown is small, this one, if this one is small, meaning that let's say very small, so meaning the HW goes up. So when HW goes up, so this H and HW, it is not same, but we can say I have to change the ink pens. So this one we can say it is not same, but it is moving. Okay, it is not, we cannot write like this, but we can write, it's not same but equivalent, something like small. But this case is very rare. Okay, it will not happen. Okay, so then we can write this, so we can simplify this. Okay, and this is the H is the thickness of the aquifer. Okay? So usually, as I mentioned from the hydraulics study, so our main purpose is to calculate the pumping test or hydraulics. Our main purpose to calculate the Q, calculate the T, calculate the S. Okay, so Q we can, okay, this one we can determine. T we can determine very simple, because T is, if we know the K, this H is the thickness of the aquifer, means depth of the aquifer. Okay, rest is the S. How to determine the S? Okay, next step is S. Okay. Okay, so this is a simple calculation here, one problem. Okay, so you can just simply explain. You can see here, this is 30 centimeters. So once you explain, actually, if we can do this, once you read it, you have to draw the figure, then it is good. Okay, but anyway, I have given the figure here. Okay, this is the figure, the same figure. Okay? 30 centimeter oil. When you say 30 centimeter oil, so meaning that this is RW. Okay, so 30. So we have to do in meter. Okay, meter, right? Then penetrate 50 meter below the static water level. So means static water level. So this static water level means the groundwater level is the same. Okay, static means before pumping. Okay, so meaning that this is the level to the aquifer. So this is the actually depth of aquifer, means capital H. So capital H is given. Okay, it is a 50 meter. After a long period of pumping, the Q is given. Liter per minute. I think we need to change to meter cube. Okay. Meter cube per second. So we have to divide by 1,000. So sometimes we need to see the what is the unit. Okay, is a meter cube per minute or meter cube per second. So you have to follow the notation. All right. Then the drawdown in the oils 15 and 40 meter. So meaning that S1, S2. Okay. S1, S2 is given. This and this. From the pumping oil, okay, so this one is the distance R1, R2, and S1, S2 is this one, 1.7 and 0.8. Actually, if we say this is the S1, this is the S2. Okay, so this is the distance R1, this is the distance R2. So determine the transmissibility. Okay, so when it's determine the transmissibility, so first because from the equation that we have here, this equation, everything is given only K. So we can find the K first. Once we find the K, transmissibility T equals KH. In this case, means aquifer thickness or aquifer depth. So once H is given 50, so we can find. So this is called transmissibility. Okay, so this is how we can find the transmissibility. So I have given the explanation, also one example. So if we practice, I think it will be clear. Okay. All right. Okay. So then asking, what is the pumping oil drawdown? What is the drawdown? Then okay, what is the drawdown in the oil? Pump oil. Sorry. Okay, so and this is off here. Okay, but anyway, I show here. Okay. So there is a, then we can once we know the age and this, we can use the, we can determine the, we can use this formula. Okay, this formula. So from this formula, we can determine the age. You can see the all informations are given except the age, HW. Okay, so when you calculate the HW, actually H minus HW is the pumping oil. Okay, you can see here this one. H minus H the pumping oil. So meaning that we can use this formula to calculate the SW. SW is the drawdown in the pumping oil. Okay, but there are some simplified version of equation. This one. So this one, there is one equation. So that equation is very simple equation, Q by SW, T by, because we have Q, we have already calculated the Q, or Q is given, is it 18? Q is given, T we have determined. So from there we can find the SW. So this is a simplified form. Okay, this we can use also this formula. Otherwise, we can use the previous one. This this one also we can use. Okay, using this also we can find the, in this case we have to find the H minus HW. H minus HW is the drawdown. Okay. Okay. Right. So okay, until now, have any questions? If not, then I will move to next. Okay, so then next one is this is that one I studied the steady unconfined. So now is coming steady confined, because we have a mainly I told mainly we have a two type aquifers, but there is another one is called leaky aquifer. So we have three types of, mainly three types of aquifer, but there are other types of aquifer that are not very good aquifer. Okay. Because in the underground we have a different types of structures. Okay. So this is a steady flow in a confined aquifer. So confined aquifer and unconfined aquifer, what is the difference? Actually, the difference is only confined aquifer, we have a two impermeable layer. One is the bottom. If in the unconfined this upper bottom is not available. So confined aquifer, we have a two impermeable layer. So this impermeable layer. So our aquifer is this one. And the difference is unconfined aquifer, we use the H. from the static water level to the bottom of this. Okay, that is H. And this one also is called aquifer thickness, aquifer depth, unconfined. But confined aquifer thickness is this one. And this one we denote by B. This is the difference. So H is not the aquifer thickness. It's H. But in the unconfined aquifer, you can see here, unconfined aquifer, H. So H is the aquifer thickness. So then when we calculate the T, we use KH. This is we use for unconfined. You can see here. Where is this? I think previous slide. Yeah, TKH. Okay. But when it come to confined, if we know the K, then our T equals this KB. K multiplied by B. This is the transmission. Okay. So other terms is look same, but the depth, the water level is not the same, because the confined aquifer, it remains under pressure. So once you install the well, so water level goes up. And this water level in the unconfined aquifer, we call groundwater level or static water level. Okay, we call groundwater level, or sometimes we call static water level. So this is called unconfined aquifer, UC, unconfined aquifer. Okay. And for confined aquifer, this water level is we call piezometric surface. Piezometric means pressure. Okay, so this surface is called piezometric water level. Okay, it is not groundwater level, it is not static water level. Okay, it's called piezometric. You can see here original piezometric surface means before pumping. Once we start pumping, then water level will drop, same like on confined. So okay, then it is S1, S2, H1, S2, R1. This is the same. Okay. Okay, then we have this similar way we can derive. So instead of Ki 2 pi xy, in this case is the aquifer thickness is B. This is the difference when we use the confined aquifer. Then we derive this equation. So then we can find the Q. So when you find the Q, you can see all H2, H1, R2, R1 is available. B is available. K we have to find from the laboratory. Okay. If Q is given, then this K we can determine, we can calculate, because from the pumping water level. Okay. Is from this diagram. You can see here. This diagram, all information is given. Q is known. If we can measure by Q some device. So let's say 1.8. This R1, H1, H2, H2, everything is known then. Once we pump, all information we can measure. We can measure by groundwater level sensor, this flow meter, we can know. Okay, once we know everything, then we can put all the value H2, H1, R2, R1, Q is given, then we can find from here K. Once we find the K, then we can find the T. So T equals KB. Okay. So we can find two ways. One is from the observation oil, another is from pumping oil. So that's when we say pumping oil, it is H minus HW. So H minus HW, actually this is the SW. Okay, this one. All right. So we can use this one. So from here also we can find the T or we can find the Q. Okay. And this is a small example observation oil S1, S2. So sometimes you can say S1, S2. Sometimes you can say H1, H2. Actually the same. Because if you know the ACE1, you have ACE. So ACE minus ACE1 is the S1. Similarly, ACE minus ACE2 is the S2. So you can determine it. Okay. Here, no problem. So then this is the how we can determine the T and A's. So I have already explained. Okay. So okay, that is a steady. You know we have open channel flow, steady flow, unsteady flow. So groundwater also we have an unsteady, steady. So just now we have discussed the steady flow. Okay. So now we come to the unsteady flow. Okay. So unsteady flow. So we have a different methods. Okay. Different methods. So first method is a test method. As I mentioned, the test is the first time who derived the groundwater hydraulics theory. Okay. Groundwater equations. Okay. Flow equations. Is the same diagram. We have a different technique. So yeah, our purpose is same, or determine the T and S. Okay. Right. So this using this simplified some derivation, we can actually determine the S, because previously we determined the T and Q. So if we want to determine the S, so we have to come here. Okay. We have to come this after derivation. We have a different model, or you can say formula. Then we can derive. So this is the Thales method. Okay. I think I explained the simple way to explain. So this is the equation coming from the this actually previously I showed the one equation. What is this? I think I forgot. Is there here or not? Okay. Yeah, this one. Okay. This is the equation. Yeah, but there is another equation is at the beginning that I showed you. Groundwater flow. Okay. This one. Okay. So this equation after deriving, actually you can see here S is the storage, T is the transmissibility. Okay. So and A is the hydraulic gradient. So groundwater actually flow depend on the storage, transmissibility, and the gradient. Okay, these three. So this equation we have a different forms. So after simplifying or solving the differential equations, okay, so this is Thales. So Thales derive this method. It's called Thales method. Sometimes it is called Thales type curve method. Okay, Thales type curve method. Okay, type curve. Okay, so simple way just to know this. So what is the equation? So this type of method is this is the equation. So where we can find the drawdown, we can find the drawdown, we can find the S and T. Okay, and this is the equation. You can see here we have the T, we have the S. So this is the S, this is the T, and then how we can find this? How we can determine S and T? This is the purpose mainly. Okay, and this is the W. So WU is the function, oil function. Okay, so this one is how we can say this one. I forgot that something is W is the oil function. It is it is something like the okay. I can remember now something that I want to. is W. This is the one relationship. You know the pumping, when you select the pump, I think you have studied the hydraulics. Okay, we have the when you buy or select the pump, so there is a pump curve, is it? So pump curve, it comes from the manufacturer. So we have a different types of pump curve. I think you have studied the hydraulics. Okay, and then we have a system curve. System curve means our system, where means we have a system, we need to pump. So we have the system. So our system curve is something like this. Okay. So then we have to choose what is the current, what is the right pump. So we choose some our matching point, is it? So in that case, we determine the Q and total dynamic head. Okay. Then we can find our, this is our system curve. So this is our system curve. Then with the system curve, now we have the our target Q. So this is the Q and this is the TDS. Okay. Let's say our TDS is maybe 100, let's say here, and this is the Q. Okay, this is the point. So now we match all the pump curve. So which pump is suitable? Then we say, okay, this pump is suitable for this. So this is called pump curve selection. So test method is similar like this. So this is called oil function. Okay, oil function, and also it's called type curve, oil type curve. This is function is this WU. So he proposed this equation. Okay, if we know the U, we can find the oil function. So this one we can determine like this. This is the U value. U value is 1, 2, 3. So meaning that 1 multiplied by 1 is this. 2 multiplied by 1 is this. 3 multiplied by 1 is. So meaning that U value is, what is the U value? Let's say if I say this one, if we say 4 and this one. So meaning that U equals 4 multiply 10 to the power minus 3. This is the U value. So when you say this U value, then we put this U here. Okay, this function. Then we calculate using this formula. Then we can find these values inside all of these values. Okay, either we can use this formula or we can use this table. Then we can find the limit. Okay. So this test method, okay. So we need this U and W. So from this table, we need a U. Once we know the U, we can find the W either from this formula or from this table. Okay, this is a clear from here. Clear now? Okay, now come to the next. After this, once we get the U and WU, we will get the some series of data. Series of data, how we can take this data? So usually you can take, let's say 1, 2, 3. Means when you take the U, you take this all and take this row. Take this row, take this row. You select maybe 1 or 2 rows, all. Okay. Then you can calculate the WU. Okay. U and WU. You can calculate. Maybe you can take this or maybe you can take all. This is the good practice. You can take random way, that is not good. If you take this way, it's fine. Okay. Then you have to plot. But there are some recommendation. I will share you the one that material, that slide I have prepared. I will share you later. Okay. Because this is not available. So I have the hard copy book. So you need to scan. Okay. So this one, I have the different version of book, different edition, first edition, second edition, third edition. So the first edition that I studied during my study time, that time it was not available. But in the latest edition, the writer, author proposed that you can use this value. Then you can find the you can find the you can find the graph very fast. This is the most recommended value. This one, these values. Maybe you can take this. Yeah, you can take this, or maybe you can take like this. Okay, so follow some system, meaning that you use this u 3 multiply this, 3 multiply 4 multiply this, so like this. So this value you can take it. Once we take this value, next step, then you can find the u and wu, is it? Then you plot it. You can plot it in the what is called this semi this is not semi log, I think this is a log log. Okay, it's semi log or log, semi log, I think. Yeah, it is a semi log because this is the log, this is normal. Okay, semi log. So then once you can plot it, then you can find this curve. So this like pumping curve. Okay, you can plot it. Okay, so that value you have to take from this table or formula. Okay, so next step, we have the observation, we have the data, is it? The pumping, when you do the pumping, we have the data for and T and S. Okay, T and S. Drawdown. Okay, we have this data, so we have to plot this one also. Another curve. Okay, so meaning that first one is the U, WU, second one is T and S. Okay, so this curve would be the similar pattern, but will not be the same scale. Okay, different scale. You can see here. Okay, so when you plot it, okay, when you plot it, you plot the same scale, means you take the same scale here. Let's say here is 1, here is 100. So here is 1, here is 100. But the line will be the different location. You can see the position will be different. Okay. After this, you have to superimpose this. This one you have to superimpose on this. Means your field data. This S and T, this is from your field data, observation data, and U and W is from the table. Okay, mathematical model. So one is superimposed, then we will have some matching point like this. Okay, this matching point. Once we have this matching point, then we will get the 4 values. We get the U, we get the WU, we get the S, and we get the actually R squared T. Actually, we have to plot here not R, not T. This is R squared T. R squared by T. Sorry, R squared by T. Because you know when we do the okay, when you do the observation well, this is the observation well, is it? So we have the okay, we have the R means this is our pumping well. Pumping well is this, so this is called R. So we have the R and then the T. So this is called R square T. And then what is the drawdown? Okay, is the drawdown. So that is R square T and drawdown. So that's what we have to put here is R square T, here is S. Another one is U and WU. Okay, so then once we match it, we will get the 4 values from here. Okay, so one we get the U, WU, we get the S, and we get the R square by T. We get this 4 value from this matching point. Once we get these 4 values, you can see here U, S, okay, S, and then R square T, and also WU. This is 4 values, 1, 2, 3, 4 from here. Once we have these 4 values, then actually we can calculate the Okay, this is the same. This one is more colorful. One is you can also do like one U and W, means when you find the U, you can calculate 1 by U. So if you do this, the curve will be opposite. If you use the U, okay, this is the difference. But you can use this one also. Some books use this one. Okay? And then this is the methodology. Once we do the test diagram, test method, we can know all the 4 values. Then we can calculate the T and S. You can see here T. How to find the T? You can see the Q 4 pi S. Okay, pi S. This is the drawdown, and WU. So from the matching point, we have the WU, we have the S. Okay, Q is given because when it is pumping, our Q is available. Then we can find the T. Once we find the T, we can find the S. You can see the S equals to 4TT, then R square U. So U is available from the matching point. This is R square T. Okay, or T R square. So we can divide it by T. So then it will come here R square T. Okay, and T is available from here. So we can find the S. So meaning that this is the way we can find the T and S. Okay, using this test method. So this is when you use the 1 over U. Okay, so these two formulas we can use. And I have given the one calculation here. From the you can see the Q is given. Q is given. So W, U, S, and R square T on the matching curve. Once we have this, Q is given. So we can find the equation. From the equation, we can find the S. Okay, this is the drawdown. So from here, we can find the T. Once we find the T, so next equation is here. U equals R square ST. So from here, yes. So S, we can find actually, we can use the another equation that used before. One is this, another is this one. Actually, this is actually simple version because one is before, another is after. So what is this? This is the S. Okay, we can calculate from here is T. Is it? Once we calculate the T, we can use this one for the S. Okay. Before this, what is so? Okay. Okay. Actually, this is the same equation that's simplified. Okay. S, because that equation is U is left side. Okay. Actually, the same equation. Yeah, same equation. U is left side. So this one, if we find this S will be R square by T. Okay, so this is where we can find the test method. We can find the T and so this is the one of the technique that you can know now. Okay. So meaning that if we want to know, because as I mentioned before, if we want to know how good is the aquifer, we have to know the T, we have to know the S, and also draw down. Okay. So T and S we can find using this one of the is test method. Actually, groundwater is a steady flow, unsteady flow. So this is the most appropriate. Okay, unsteady flow. Steady flow is a simplification. Okay. So we use the test method. So using test method, we can find the T and we can find the S. Once we find the T and S, actually, once we find the T and S, this data you can use for forever for particular aquifer. You don't need to determine again and again. So using this value, later you can do the modeling, whatever. So next time, if you install the new table that same area, then if you want to know what is the Q, then this T and S you can use it. You can find the Q. Okay, because the previously that I showed the formula, all of this formula here. This formula you can see it. Q. Let's say we don't have the flow meter. If we want to know what is the pumping rate, T is available, drawdown is available, we can find the Q from here. Okay. Once T we have available here, then after this we can come to the here find the S. But S we cannot find here. S is not here. Here we can find only T because this is the steady flow condition. So if we want to find the storage coefficient, we need to use this method. This is the one. Okay. So I explained the another method. This one is a little bit complex. Okay. There are another 4 methods. 4 methods. So for that one method is easier and simpler than this. So that 4 method is like this. This data is available. Means once we have the field data, means in the field we collect the S, R, and T. Okay, so I think you're very clear now. So this is the pumping oil. So this is the original water level. Then we have the observation oil. This is the observation oil. So once it start pumping, water level come down like this. So meaning that T is the time, 0 time 1, 2 like this. And then what is the SW? So meaning this one. What is the X1? So meaning that this one. What is the S2? So this is the S2. So these are the data we collect from the pumping test. Okay. Once we collect this data, so we can do this. First is this method. So second one is called Cooper-Jacob method. Okay. So Cooper-Jacob method, he proposed three methods. First one is time and drawdown. So meaning that we just use the T and S drawdown. So this drawdown is not in the pumping oil. It is observation oil. So pumping oil is SW. So when I write S, it is means observation oil. Okay, like this. So then he used this time and this. It means with the time, what is the observation oil drawdown? We just need this data. This simple method. This is more simple than simply. So then he proposed this phase method. When we use this one for this condition, when T is more than this or E is less than this, he proposed that this first two term we can replace for WU. We don't need other terms, just first two. But so he simplified. After simplifying, means this he doesn't use this one. Okay, he removed. So just he used the first two terms. So these two terms WU he replaced here. Okay, you can see here S equals Q40 and this. After replacing, he simplified and provided this. And this equation you can see here, S is drawdown. 2, 3, Q is the pumping rate, T is the transmissibility, and this is E, and this S is storage coefficient. Okay, so from here we can find the T and S. One equation is this, another equation is this. So this is the S, and this one is S2 minus S1 means when S equals to 1 means observation oil 1 S1, when observation oil 2 S2. Okay, so then we just do the subtraction, then we can find this one. Okay. So he proposed this equation. You can see this equation and this equation. So this S2 minus S1, we can write the changes of drawdown. Okay, we can say. Then it's very simple. You can see here. So we have a pumping test data. So from this pumping test data, we have a S and T. Is it? So this T and S, we plot it here. We plot here. So this one is the T. This one is the S. Drawdown. Just plot. It is a semi-log. So this is the log, and this one is semi-log. This is the normal. Okay, normal. So semi-log. We have to use the semi-log paper. Semi-log paper. So when you plot in those on the semi-log paper, so we'll find some point, then we make the straight line like this. You can see the graph here. This is the straight line. Okay. So when you find the straight line, then you propose this. You can see this equation T equals 2.3 Q 4 pi S. This comes from here. This one. Okay. And how it comes? Okay, you can see this equation T2 minus T2 by T1. T2 by T1. This log 10 T2 by T1. Okay. So he transferred this one like this. Okay. I think I write here, then you can understand easily. Okay. You can see this S2 minus S1. So this one S2 S1 means del S. Okay. Then 2 3 by Q, 2 3 by Q, and 4 pi T. It's okay. And this log 10 T2 by T1. Okay. This one is meaning that this one. If we take one log cycle, this one, okay, one log cycle, T2 by T1, okay, is here. Okay, so then okay, just a minute. Okay, del S is del S is del S is actually you have a log cycle, is it? This is the one log cycle. This is the one log cycle, this is another log cycle. So del S is the drawdown S1 difference, S1 and S2 difference is del S. So this is the drawdown for one log cycle. This is the one log cycle. What is the drawdown difference for one log cycle? So that is defined by the del S. All right. This is defined by the del S. And when you take this one, so this log cycle, so what is the value for this? 10 is 100 and this is 10, is it? If we set log cycle, if we take this cycle and this cycle, so meaning that if I say T1 is 10, T2 is 100. So T2 by T1 is, sorry, T2 by T1 is 100 divided by 10. So 100 divided by 10 is 10, is it? 10. And our, here is our log, is it? This is our log 10. Log 10. So log 10 and our T2 is T1, it is 100 by 10. So it is 1. So this one is 100 by 10 is 10, is it? So 10, 10. So if with our base and base is the same, so this one is T Q 4 pi T. So this meaning 1, is it? This one, base same. So it is 1 for 1 log cycle. So any log cycle is actually the same. If I take this 1 and 10, T2, T1. So T2 is 10, T1 is 1. So also value is 10. So for 1 log cycle, T2 by T1 is actually 10. Once we put this in the log here, it becomes 1. So our this formula simplified by this form. Okay. So meaning that del S equals 2.3 Q 4 pi T. So that's why actually this is the equation 4.79. Actually, this equation is simplification of the previous equation. This one. This one is a simplification of 4.79 previous equation. So if we simplify this one, what is this? How to calculate this one? So meaning that T equals our 2.3. So Q is pumping rate, we know it. 4 pi, pi is constant, and this del S is the value for one cycle. You can take any log cycle, either from here, or maybe you can take from here. So meaning that this value, or maybe this value is the same. Then you can put it here. So this value is we can find from here. So once we can find here, then we can know the what is the T. Once we know the T, then we can find the S. Okay. And when we find the S, there is something we need to know how to find the S. Okay. You can see here. This thing, how it comes, this equation, how it comes. Okay. You can see it from equation 4.78. Okay, 4.78, this one. S equals to 2.3 Q 4 pi T log 10 this. This equation, we took the one log cycle. So this equation we can simplify when this one equals to 1, this part. When this one equals to 1, I remove here. Let's say this one, this part. This part equals to 1. When this part equals to 1, log 10, 1 equals to 0. If log 10 equals to 0, so meaning that the drawdown will be 0. Okay. So when drawdown will be 0? So drawdown will be 0 when T is 0, or in the initial condition, very initial. Okay. It is not at the T0. It is a T0, but when? What is the time? Okay. State, but we need to find the time. So that is the condition here. You can see here. What is this? Next page here. Here. You can see this one. When S0, this log 10, this one is 0. When log 10, this one is 0, meaning that this part is 1. Okay, this part is 1. When this part is 1, so from here we can derive this equation. And when you derive this equation, at that case, this T becomes T0. And this T0 is the time when drawdown is 0. Okay, it is drawdown is 0. So we can say, so maybe at the beginning, actually not the beginning, it is just near to the beginning, means after pump started. Okay, it is a dynamic condition, means once pump started, when okay, it takes some time, maybe a few seconds or less than minute. Okay, that is okay. So that one actually, once we draw this curve, then we extrapolate, then this line will join with the axis. Okay, so that is the point actually drawdown is 0, because here is a drawdown, this is the drawdown. So this is drawdown is 0. You can see we extrapolate, here is 1, but 1 we extrapolate, this is drawdown 0. Once you find drawdown 0, you come down here. This is the time. This is the time it's called here. This is the time is T0. So then we have to use this. Okay. Little bit complex, is it? Clear or not? This part. If you understand this one, next 3 is the same, almost the same. Only the different here is a time drawdown, there is a drawdown and radius. Another means drawdown and radius means this is the T and R. Sorry, no, this is R by S. Radius and drawdown. Another one is R squared T and S. And this one is T and S. So these three methods is the same way. Okay. So here is the understanding is that first one, when you find the T, I explain again, it is easier. When you understand, when you find the T, we find the T, we simplified by for 1 log second. 1 log second. When you take 1 log second, this one, so then T2 minus T2 by T1 becomes 10. And then we put the log 10 and 10. We can put the T2 by T1 10, so it becomes 1. So when we put the value 1, the equation simplified by this. And from here we can find the T. Second equation is the same equation we can simplify when drawdown is 0. So meaning that we plot the T and S. After this, we extrapolate this line and join to here. Then we come down. So when you go to the Excel, you can extrapolate it easier way, because nowadays we can use the Excel. Okay, no need to use the hard copy one. You can use by Excel. Okay, so you can this. Then you can find the T0. Then this T0 you can put it here, and this equation. So you don't need to use this. This is some simplification process. Okay, so I don't explain all simplification because it need long time. So here you can find the S. So this is the second method. Okay, and then you can, I have given the one example you can find from this here. This is the T and drawdown. Okay, T and drawdown. So this is the practice also, and produce this. You can find the S and T solution. Okay, so this data you have to extrapolate. Okay, you have to extrapolate like this. Then this one will be, this is time for T0. Okay, so then you have to use this T0 is here. You can see this value 0.358 is this. So here, so less than 1. Okay. Okay. This is S and T. So second one is distance drawdown. It's the same thing, but you have to plot only R and drawdown. Okay, because we have the data from the pumping oil. So in that case, you need observation oil, maybe 3, at least 3, because this is the R. So meaning that this is the pumping oil. You have 1, 2, 3 at least in this case. If you don't have more observational, so you cannot use this method. And then similar way, there is T and T1. Here is R and R1, R and R2. So you can simplify it. Then you can find this, and you can find this. So in this case, instead of T0, you have to find the R0. Because when you plot this data, so you can find this way. This is the R, this is the TS. So then you have to extrapolate this and go 0. So from S0, you can find the R. So S0 means where is the long way, because our observation well is here. So S0 means the capital R, okay, a radius of influence. So this one we can determine from this data. Same for 1 second and 4, okay. Then this is the example given. Xol oil is the oil, this is the observation, okay, draw down. Then you can plot it. So this example is given. So once you practice, I think you can understand. If you don't understand, confused, yeah, please contact me. Okay, please contact me. I will explain. Okay. This is the demo. So next method is This one is some equation is given. So this equation we used before. You can see, can remember T by this and something S divided by this XW. Third method is the distance drawdown method. So it means time distance drawdown. So in that case, you need a 3 observation well. So meaning that you have to collect the T, you have to collect the S, you have to collect the R, also T, S, T, R. Yes, yeah, these three. Yeah, means all together. First method is T and S. Second method is S and R. Third one is 3 together. So meaning that this one is R square by T and here is S. Once you plot this semilog, it's all semilog, then you can find the similar way. You have this equation like this. You just follow this equation. S equals to this, T equals to this. So when we say S, so this is the del S. What is this del S? Del S means we have the graph. Okay, we have the graph like this. So the log cycle, you take the one log cycle. What is the difference for one log cycle? What is the drawdown difference? That is called del S. Something like a slope, actually. It is a slope for one log cycle. That's all. Okay, like this. So similar way, you have to find the T0. In this case, it's not T0, it is T R square 0 because our x-axis is T by R square. Sometimes it is used T R square, sometimes it is used R square by T also, because if R square by T, I think graph will change to like this, opposite direction. Also possible. Okay, so then you can use this formula, this one and this one. Then you can find the S and T. Okay, so this is very important that I showed this some method. Okay, so mean that confined, unconfined. Okay, you can use this, right? Yeah, this is the some definition. So this is another example. Okay, this one is not important. Actually, I put it, if we have a time, I wanted to explain more, but no time. So what I want to say, what we until now, what we determined, at least we have got some understanding. Actually, when we do the modeling study, when you do the groundwater study, okay, so one way is we can do the pumping. Pumping, when you do the pumping study, we can get the some specific small area. Let's say we have a T-wall. So around this T-wall, what is the aquifer type? We can use this. Okay. Let's say area is maybe 1 kilometer square or 500, like this, 500 meter. So within 500 meter, what is the characteristics of the aquifer or whatever? We can know by pumping test. Means we have installed the pump, drill the pump, we can know it. But if we want to the regional modeling, means let's say entire Sardan areas, okay, Sardan Kazan large areas, or entire water basin or watershed. Okay, when we study, then we have to go for modeling. So maybe we do the 3 or 4 certificate order. We do a similar kind of study. So we get all the information that I explained until now. Okay, your aquifer thickness, geological log, then K value. Okay, if K value is not available, we can determine by pumping test also. If we know the Q, then we have to calculate the T, we have to calculate the S. So this, all of this information, also the pumping test data, all of this data we need it. We need all of this data. Once we have this all this data, then next one, let's say you want to study the groundwater potential in your watershed. In this watershed maybe 1,000 kilometers square. Okay, so 1,000 kilometers square. Now you want to study what is the groundwater potential, how much water we can export, how much water we can pump from this watershed. Okay. So in that case, actually, if you just use the one well here, This is not a good. You can do the modeling. You can assume that, okay, I have one well. I assume that everywhere is the same. You can do this is called lumped model. Like when you do the hydrologic model, we call lumped model. Is it one station rainfall is same, but actually the rainfall is different places. So here is the same. Instead of the rainfall, we use the few pumping station, pumping oil, at least like this. I don't know how many, but 3, 4, 5, depending on the areas. If we know this, like this, like a semi-distributed, here one, here one. So until now, what we have studied this pumping. So if we do this, we have this information. This all of this information we can put in the software. There is a software available, as I mentioned before, ground mode flow. Okay, one is mode flow modeling, GWM. This software we can use. Maybe other software is available, but this most popular is this two. Okay. Then you can use. Then you can know the whole watershed. What is the groundwater potential? Means how much water you can pump. Okay. So now, if we know the groundwater, how much you can pump, this is called safe pumping, safe yield. Okay, without any environmental negative impacts. Okay, you can get the groundwater, and you have the surface water. So this surface water and groundwater we can use conjunctive. That is called actually conjunctive use. The term sometimes you can find conjunctive. Conjunctive use means use surface water and groundwater together. Or maybe when surface water is available, you can start pumping ground. When dry season, no surface water, no rain, you can pump the groundwater. So this is called conjunctive use, or sometimes we call integrated water resource management. So integrated water management is not only the surface water. That is not integrated, just surface water. Okay. So that's why this groundwater knowledge is very important. Okay. I uh, encourage. I I like many students should study this. Okay. Otherwise, one part is like you have a two hand, one hand is strong. Okay. But maybe today is no problem in Malaysia, but in future you have to go no ways. Okay. You can guess now. And by day time is passing, water resources is going scarce. Okay. So you have to come here one day. No ways. You have a water, but you cannot use it. When you cannot use, you have to alternative source groundwater. And groundwater is a huge. It is huge. No worries. It is available. Just you have to pump with the knowledge. Okay, that's the thing. All right. I think your water engineering course you should have groundwater course. Okay, you can propose. Okay, otherwise not complete. Okay, so this is the distance drawdown. Okay, so actually now this is the at least two. This two is the main. Actually, normally we say unconfined and confined. There is another type is called leaky aquifer. Okay. Our time is finished. Okay. So leaky aquifer, I have provided this here. This another one is another method is called test recovery. This is another method. This also confined, unconfined aquifer. You can use it for this. Test recovery means that when you start the pumping, this is the original. I just explained few minutes, then we stop. This is the original groundwater level. So when you start pumping, so this water level drop to down, is it here? So this is the first four methods: phase method and T versus S, R versus S, and R square T versus S. This four method we have discussed. So this is the another method. This is called phase recovery. The original one, phase recovery. Phase recovery means when the drawdown come here, then we stop the pump. After we stop the pump, this water level again will recharge, go up. So we monitor this, how fast, this recovery, okay? How fast this recovery occurs. We monitor this water level after stopping the pump. Because after this water level like this, So once we stop the pump, so then water from this side will enter this area, and it will refill like this. Say we pump for 4 hours, and drawdown comes here. But within 4 hours, it will not return back here. Never. I have I have I have I have done the experiment myself. I know. I never I never I never find the water level again. It was always take some time, long time. If we don't pump for a long time, yeah, it can be. Or maybe some rain comes. Because when you pump, you have you have you have taken some water, actually take out some water. Okay. Like when you feel hungry, means something is removed from your body or it is burned, you made the energy. Is it? From food, you made the energy. So that's why your stomach is empty. Now you have to eat. Then you can recover actually, refill again. So in this case, it's not like this, but in this, water will come, but this water flow is very small. It is, I think, 0.1 meter per second or 0.01 meter per second, very small. It's not like open channel flow. So water comes from here very slow. So it takes long time. Okay. So this is called recovery method. In this recovery method, is like this. This is called drawdown. So when you stop pump here, so this water level come up, and it doesn't raise raise to zero position uh, within short time. It takes some long time. That's why you call pump on, pump off. This is the process. Okay. So you get the data. This is called data point. Data. This is the data point. So this is called residual drawdown. This one is something called some drawdown. We not this called residual drawdown. So then we can use this formula. We plot this data. We plot this data. Then use this formula. Then we can determine. Just understand the fact, and then use this formula. I have put this formula. This is the theory part. This data is like this. This is the T time. This is means recovery time. Recovery time means the time from here, not the pumping one. Is here. T prime. Okay, T prime. Okay. So this is called T prime and S prime. Recovery. So now T prime. So T equals your original pumping time is you can 1440 means almost 1 day plus T prime. This is the total time. And T by T ratio. So T prime, we have to calculate the T by T ratio and draw down. So this T by T ratio and draw down, we have to plot. So this time is 14440. This one means this time. This time, T1, when stop pumping. So T plus T1 means this time plus this time. Okay. Okay, sorry, just I want to stop after this. Okay. Uh, yeah. Then T by T ratio. Yeah. And yeah, this is the thing. We have a plot the same as semi-log, T by T ratio, and this residual. Here is not drawdown, residual drawdown, that recovery drawdown. Okay, then we can put we have to put this data extend to here, and we can find the when the T by T1 is 0. Okay, then we can find this. We can find the T, then we can find the S. S is here. Okay? This is the S. So when you find the S, we need this T1 by okay, T by T1 0 or something like this. Or if it, yes, somewhere it is ever. If not, then we have to find the T1. T1, this one is equation like this. I studied actually this all the formulas I memorized. Okay, but now I forgot everything. here, this one, T, this one, T S square. So this formula you have to use for S. Right? Yeah, so from this data, this table, we can find this all this level, same as like other 4. Okay, then you can find the, so this is the 4, 5, 6 method, you can find the S and T. Okay. We have some other method, but this method, there are many people now they are developing because many people are studying. So this is another method we can use it also. Okay. People are trying to simplify it. Okay, like this. Okay. But if you study now, I think something you understand. So he simplified the first method, the Thales method, first one, he simplified. He used WU and WU, he used the AFU. He proposed a new one. So instead of W, use the AFU. So when you install the AFU, it becomes, it doesn't the matching. It's a simple curve like this. Okay. Then can find the T and S. The purpose is S and T. Okay. Can find those. And this is the example. So yeah, this is the, yes, same one. Then another one is a leaky and artificial aquifer. Okay. This, only difference is that I just explained. You can see here, this is the unconfined, this is the impermeable layer, but this is not impermeable, fully impermeable. It is semi-impermeable, means that water from the upper layer, unconfined, can penetrate and can come to the confined aquifer. This is called leaky artesian aquifer. So this one is called permeability for K1, K prime, K prime. And this layer is called B prime. This is a B. This is a B prime. And this is the some formulas available. But this one is not necessary now. Maybe you can, when you all the terms, terminology now you are familiar. So what I understand, if you study this one, you can understand. If you like to study, then please. If you don't understand, then come back to me. So in that case, we have to use this kind of what's called uh, this kind of is called type cup, because previously it was WU, here is U and RB, because it is a complex aquifer. Okay, there is, here was previously, here we use WU, but here is WU and RB, URB. So this B is the thickness of the impermeable, semi-impermeable layer. Here is 1 by U. We use U. Okay, so there's some difference. Otherwise, the formula structure is the same. So once we have a matching curve, these are different types of, like a pipe pump curve, different types of pump curve. Then our system curve means our field data. So our field data, we will, let's say our field data is this. So this field data and this curve, when you get it, we from here we can get the 4 datas. One is this, another is this, another is S and T. Okay, and then we can solve this, and then we can find the S and T for the leaky artesian again. Okay, so sometimes if when you do the modeling, if you feel that your modeling you cannot get the good results, maybe you can think for the leaky artesian aquifer. Maybe your aquifer is not confined, not unconfined. It is a leaky aquifer. Okay, it can happen. Okay, that's all. I think this is the hydraulics part. Okay, once we have the hydraulics, actually, I have given some examples. Okay, I think I want to stop things. Actually, there is a next what I say. I wanted to explain, but actually, as you can understand now, it is very wide topic. Okay, so I just finally want to say that, okay, you can see the content. Once you have this hydraulics, okay, Okay, so yeah, shortly I will stop. And then I'll come back to content and summary. Once you have a hydraulic part, the hydraulic part is very important where we can characterize the aquifer. When you characterize someone, then you can know the behavior. So simply you can do many things. If you know the someone behaviors, so you can know how to treat. Once you know this, you can do the design the oil. You can now design the table. Okay, because you know the SNT. Once you know the SNT, so now you can find what is the Q. Right Q means shape Q. Then you can pump it. So that's called design part. Once you design the pump, then you have to have the management. Then you have to do the management part. So management is your T wall, also your aquifer. Means your pollution. You have to stop the pollution. And then your pumping. Your pumping should over pumping. So meaning that shape always should be maintained the shape yield. So that's why you have to continuously monitor the observation oil. How the drawdown situation, whether drawdown is permanently depleted, okay, or drawdown is the same every year. Okay, every year you can see the drawdown, there is no changes. Okay? When you monitor, the minimum one is the same. Sometimes up and down is okay, but there is a minimum. Minimum doesn't go drop. If minimum doesn't come drop, means this is a problem. So you have to care about this. So this is the management part. And then you have to do the modeling. So modeling actually you need to teach all of this. Okay, when you do the modeling, you have to do for the large areas. So you need a data. That's I mentioned, like a rainfall station. You can do the like watershed modeling, surface water runoff modeling by one rainfall station. You can put 3 rainfall station, 10 rainfall station. So when you have a more rainfall station, your rainfall station is distributed. Your surface means runoff estimation or prediction will be much better. So same here, when you have this, your prediction will be much better. When you have number of oils, okay, number of observation oils, your monitoring will be much better. Actually, when you do all of these things, you need the rainfall, you need the other climates, and this all of this you can use in the integrated modeling, and then finally you can know actually what is the total water source you can safely use or farm, or you can get from your watershed, from surface water, from groundwater, and then how we can use this water. When you have a surface water available, you know don't need to pump groundwater. So this time when surface water available, you know the reservoir. We have more rain we use, and some water, excess water we store in the reservoir. Then dry season we use it. So groundwater is the same. When you have rainfall, you have enough surface water. Your river is full. You have enough rainfall. Don't use pumping. Keep it so your groundwater will be full of recharge. When dry season will come, you can pump the groundwater. Then once rain start, you stop the rain. So this cycle will be continuing. So I don't see any problem for groundwater pumping. Okay, so this is my conclusion to all of you. Okay, yeah, maybe we can stop now. If you have any question, short question, because time is over. Thank you for your attention and patience. Okay. Any questions, short questions? Yeah, you can have many questions. You can ask me now or maybe later. You are welcome if you like to discuss sometimes. No worries. My office is in the level 3, and this is my contact address you can find here. I think this slide is available with you. If you like to study, there are many books are available now. You can study any books. I hope if you study, you can understand now. But I follow this book. Okay, so how to show you? Sorry. I can follow any book, but this book is quite good. Okay. Um, is here. Okay. Okay, so how? Sorry, can you see this one? I'm not sure. Yeah, it is showing like a reverse. Okay, so this is a groundwater. Okay, I will send the reference. This one. This is a, maybe I can write here. You can find, but this book is soft copy is not available. Is the problem? Okay, I just write here for the reference. So this one is this is a book name is Groundwater. So it is written by S.M. Raghunath, Razhna. I like this book because during my when I studied Groundwater, we followed this book, but we followed the first edition. So now we have, I think, fourth edition also available. So this one I said third edition. I think fourth edition is available. If I find, I will buy it. Okay, but soft copy is not available. Is the thing. Okay. So this is the book, but you can study any other. There are many books are available. Okay. This is the books. Okay. So do you have any questions? That's all from me. But yes, but I'm sorry because because the mainly actually the focus was the groundwater hydraulics, but I had the slide also design how to design, but no time for this. Okay, so maybe in future if you have any, yeah, let's try to understand this hydraulics first. Okay. But I have given some step by step how to design the groundwater. After hydraulics, I don't know whether you can do or not. But I'm very old actually. This one actually I studied almost after 20 years. Before in between this, I never taught this subject. Never. In my department, we have the subject, but I requested, okay, you can give me, but department didn't give me this subject. Someone, my colleague, yeah. Yes. So in that case, I'm happy that I got the some invitation from Dr. Thank you. Actually, I don't teach actually this thing. I just share my understanding. And sometimes I recharge my knowledge. Okay. This is the that's why I was interested. Okay. Without this, I would not read. Okay. So that book I showed you before your lecture, I just studied all of this book. So meaning that I reviewed my knowledge. This is my advantage and my benefit. Okay, that's all. So anything from you? Yeah, if you have any questions or something, you can contact me or can discuss later also. Otherwise, we can stop because time is over now.
Hmm. No, doctor. All okay.
Okay, thank you. So maybe if I have a recorded one, then I can share it with you later. Yeah, I will see first. That's all. Without, I'll not do any editing. I will send as it is. Okay, so if no questions, I think you will be happy to stop, is it?
Okay. Thank you, doctor.
Okay, welcome. So if
Okay.
you have some any questions, something, yeah, you can contact with me. You can come to my office. Welcome. Okay. Okay, see you then again. Because I don't know any of your face. So when you see me, you can say hello. Okay. Okay, see you then.
Thank you, doctor.
Okay, welcome.
Thank you, doctor.